Okay, that's a wonderful start opening ceremony every week. I can act tasks, connect the world and the universe. So this week will be the 12th week for this wonderful task. So what will be going on? Got to this task, just show you some lovely face. But before we go to the task, I need to give you some advertisement for the event will be going on recently. So next week we will have a big event. It's Mind 2020. That's an international conference for young science program. So we have totally 54 who will be get on the stage. So since July 7th, the Tuesday, Wednesday, and Thursday evening, every evening 3 hours, we have cover all these 45 young scientists to deliver lectures, and we will find the winner. So who will win the title for the Mind Young Scientist Award is will be delivered on the next Friday. It's July 10th. So award ceremony will be in the end of next week's ICAX task. So this event is free for registration, but you must register. If you register, even through the website or scan the code, it's quite easy. Just input a few informations. So, but you must to register. Then you can join the meeting. So that's very important. Please do the registration right away. If you need some more information, then you will go to the website. There are plenty of the information on that. Okay, and this week we start. Yeah, we have a wonderful Friday. As the same, as amazing as before. So this week we all have the adventure from micro nano to atom. So what will be going on? Who will give the talk in this week? There are two superstars. One is from US, UT Austin, Deji. Another one is Tahik from Europe, France, beautiful city, Paris. And both of them will tell us the stories in micro nano, even go down to the atom. So our guest hoster is another superstar in China. His name is Tao Li, as from Southeast Universities. I met this guy, 2 years ago. He delivered wonderful talk at American 2010. 18, yeah, he wins the title for the Young Scientist Award. So that time I say, okay, amazing. Where did he from? Before he came to Southeastern University, he was studying with Deji. So that's a link by Deji and Tao Li. So now that stage is go to Tao Li. He will introduce our first speaker, Deji from UT Austin. So Tao Li, please.
Okay, thanks, Alice. And hi, everyone. My name is Lita. As Alice already mentioned, I will give a brief introduction about Deji. Deji, he received his PhD degree from Professor Philip Wang's group at Stanford in 2009. And he's enrolled faculty full professor at UT Austin, as Alice just mentioned. His research focuses on the 2D materials and nanoelectronics, nanotechnology that pioneering device innovations from lab to applications. And Professor Deji Akinwand had won numerous awards, including the 2017 Humboldt Research Award, the U.S. Presidential Early Career Award for Science and Engineers, called PCASE, and the Gordon Moore Invention Fellow Award, the IEEE Game and North Graphene Prize, the IEEE Early Career Award on nanotechnology, and of course the NSF Career Award, DoD Young Investigator Award. I will not continue, otherwise we're going to just listen to the list for the rest of the 2 hours. So his research achievement has been featured by Nature News, Time Magazine, BBC, Discover Magazine, and many other media outlets. He has served as the editor for the IEEE EDL, Electronic Device Letters, IEEE Proceedings. He is now current editor for the Nature 2D Materials and Application, which has an impact factor close to 10 now. He chairs the 2020 Golden Research Conferences on the 2D materials and the 2019 Device Research Conference, DRC, and the 2018 chair for the Nano Device Committee for the IEEE IEDM, which is a very prestigious device conference. He is a fellow of American Physical Society and a senior member for the IEEE. Okay, I think that's the very brief summary for Deji, and we will let him to start his talk.
Thank you very much, Li Tao, for that generous introduction. So today, it's really my great honor to be speaking here in this forum. First of all, like to thank the organizers, Professor Ali Zhang, for inviting me to speak. And for those of you that may be interested in the broader area of our work, you can find my group website below. I welcome you to visit the website, and do feel free to send me an email accordingly. So today I'll talk mostly about some of our recent electronic adventures with a class of materials known as 2D materials. I'll highlight some electronic applications at the atomic scale and also at the micro scale. So in general, we're an engineering team. So what that means, we do research that starts from science, take ideas from the lab, new ideas, and try to bring them towards new technology to benefit society. So in practical terms, our research is very multidisciplinary. We work on nanomaterials, new nanomaterials. We partner with companies to develop methods of growing these materials. We also work on nanoelectronic applications of these materials. And so I'll speak a lot about electronics. And then from time to time, we discover new phenomena. So that means we engage in science of these nanomaterials. So I know that this is a very broad audience. So let me use this opportunity to introduce you to the class of materials that we work on. These are known as two-dimensional layered materials. And the basic property of these materials is they are very strong bonding within the plane. So they're very strong in plane, but they're very soft out of the plane. So the most popular example of this class of material, these 2D materials, is known as graphite. So graphite is very, very common. We've known this for over 1,000 years. And basically within the plane, it's very strong. But because it's soft out of the plane, you can remove one layer of this honeycomb arrangement of carbon atoms. You can remove that one layer, and that one layer is what we call graphene. So this is very similar to, let's say, a stack of paper. The paper is, of course, very strong within the plane, but it's weak in the stack. So it's very easy to release one sheet of paper from the stack. So graphite is a nano scale example of a stack of paper. And so even though we've known about this 2D materials for quite a long time, actually the interesting physical properties of this material, we're just learning about it in the last 15 years, especially when you go to a single atomic layer. So graphene was, should I say, rediscovered in 2004 by Guy, Novoselov, De Hare, and others, where they show that it had extraordinary physical properties within the layer. So that resulted in the Nobel Prize for Guy and Novoselov. And this graphene is known as a perfect honeycomb structure, and it's a conductive material. And then about 5 years later, the Columbia University group showed that there's another honeycomb structure. In this case, it's a compound material of boron and nitrogen. We call this HBN. This is an extraordinary insulator, very different to graphene. And this, again, revealed that there's a lot of interesting physics in this materials. And then a few years later, Andreas Kies and others show that you could also have a more complex honeycomb structure. In this case, it's a honeycomb sandwich between molybdenum in the middle, the black atoms, and then sulfur at the end. So this is molybdenum disulfide, or MOS2. And unlike graphene or HBN, this MOS2 is actually a very, very interesting semiconductor, the thinnest semiconductor that we know about. And then other kinds of honeycomb structures have been discovered. One of them is phosphorine. This is a pocket honeycomb structure, and this is a very, very high mobility semiconductor, so very interesting for high speed applications. And we showed in our lab with Li Tao and others that you could also make devices from buckled honeycomb structures. So, and this is a topological material made out of silicon atoms. We call that silicene. So now there's no point actually keeping count of how many honeycomb two-dimensional materials that there are, because there are thousands of layered materials. So for some of you students in the audience, there's a lot of opportunity for research and development in this two-dimensional materials and electronic space. So before going into a lot of technical discussion, let me just give you some of the everyday ordinary uses of these two-dimensional material. These ordinary uses don't rely on these extraordinary properties that have been discovered in the last 15 years. They're just based on its basic softness of this material. So for example, graphite, all of you are familiar with the pencil. The very reason why you can write with pencil on paper is because the material is soft, as I mentioned in the introduction. So this is a very common example. Another example is batteries. Lithium-ion batteries often use graphite in their electrodes. So you're all familiar with that in your mobile devices. Hexagonal boron nitride is a very popular material used in cosmetics, foundation, and makeup. And it's very useful because it absorbs the oil from the skin, so it gives the appearance of a very smooth and young appearance. MOS2 is a very popular lubricant. It's used in many applications, and one of those is in motorbicycles. So even though these materials may sound new to some of you today, but actually you're all familiar with them through their ordinary applications. So what are their extraordinary properties? Let me use graphene, which is the most popular of these materials, as an example. So graphene, as I mentioned, has been enjoying a renaissance, a rediscovery since 2004, 15 years ago. And so a lot of papers have been published in recent years, tens of thousands of publications corresponding to about 60 papers per day. So with this amount of publications, a lot has been learned about these materials. For example, it's the highest mobility electronic material, so electrons travel fastest in this material. This is very important if you want to get very high current or electricity at room temperature. At the same time, it also offers the highest thermal conductivity, so heat travels very fast in these materials as well. So it's good for heat management in several devices. It's actually nowadays used in smartphones, in the back of the phone for heat dissipation. It's also one of the most transparent materials. So it's finding applications in transparent conductive screens. In fact, some smartphones and displays have used graphene as their conductive screen. And this material also offers the largest mechanical strength. It's stronger than diamond, so it finds a lot of applications as well. So because of a lot of the investment, billions of dollars of investment in these materials, there's a lot of opportunity and pressure to translate these extraordinary properties to new applications and new technology. So let me spend a few slides just to give you an idea of some of the areas of research using these materials in the last 10 years. And because there's a broad range of applications, I'm just going to focus on the electronic type of applications. So the most popular of this and the one that has enjoyed the most effort are transistor applications, because one of the main objective of transistor technology, the microprocessor, is to make the transistor smaller and smaller. And transistor, billions of transistors are in your normal microprocessors. So the smallest transistor you can make requires you to use a very thin material like a 2D material. So this was already recognized more than 10 years ago that this materials would be very good for transistors. The very first work was done by Max Lamy in Aachen University in Germany, showing that graphene could be useful as a field effect transistor. So they were able to achieve a mobility of around 5,000. Mobility is one of the main metrics that you use to judge a transistor. So this is about 5,000 is about 10 times higher than the kind of mobilities that you have in silicon, which is what is used in your microprocessors today. So they also highlighted the importance of interfaces. So you could get very good current versus voltage properties without a top gate interface. But as soon as you put an additional interface, known as a top gate, the properties degrade significantly. So that catalyzed further research, and one of those was by the Columbia University group, where they showed that in fact, to get the best graphene transistor properties, the best interface is another two-dimensional material known as hexagonal boron nitride. So in fact, you get the best friendship, or should I say the best marriage, when you have graphene married with boron nitride. And so that results in very, very wonderful transistor properties, mobilities are greater than 10,000. So this is among the highest transistor mobilities ever observed. So there's a lot of research continuing on transistor technology today. Another area is flexible electronics, where we have been particularly very, very active. The idea is these materials are very thin and transparent, and they're also very strong. So you could put them on plastics or paper or glass. So we did the first work using this synthesized graphene and showing flexible devices. This is on polyamide or Kapton tape. The main thing is this took us actually about 15 months. The student really failed many times before it became successful in making this. But after it became successful in making this, it could make this flexible transistors within 2 weeks. Our initial devices were not very great. So I showed in the previous slide, you could get mobility of 5,000. So our initial mobilities, which you want to be as high as possible, is less than 1,000. So it was not the best. And then we realized one of the reasons is on a flexible substrate, you have a lot of thermal issues, because unlike a silicon substrate where when you pass a lot of current through the material, the silicon substrate can help you to dissipate the heat. In a flexible substrate like plastics, when you pass a lot of current through this material, there is nowhere for the heat to go. So after a while, you have Joule heating issues, and then you have melting of the plastic. So you have an irreversible damage to the device. So we said, okay, this is a major problem. How do we solve this problem? One way to solve this problem is by using thermal management materials. So HBN, which I mentioned earlier, hexagonal boron nitride, is actually very, very good thermal conductor and an electrical insulator, so it can be used as part of the transistor gate structure. So you have graphene on the top that is carrying the current, and you have HBN that is managing the heat. So if you have a thick enough HBN, you can isolate the heat from the very sensitive plastic. So doing this, we could now get very good performance, and we could get the record current density. That means how much current you can pass through the material per unit area. And so this is a very promising result. Then another option is using flexible glass. So this was a collaboration with our partners at Corning, the glass company. And this glass substrate has good thermal conductivity. And so you could make very, very high frequency graphene transistors operating at 100 gigahertz. So that's the highest so far on this glass substrate. So a lot of research continues using this graphene for flexible. You can also use other 2D materials for flexible transistors. So I mentioned earlier, MOS2 is a very good semiconductor. So semiconductors are the ideal materials for transistors. So the first flexible MOS2 was done by Takenobu-san in Japan, where they showed you could put this again on a plastic substrate, and you could use a liquid electrolyte as your gate, and you could get good performance. It's not that great compared to graphene, but still quite good for the first generation, mobilities of 3. So we felt that we could improve upon this work. So by improving the interface, I mentioned earlier, interfaces are very important. So by improving the interface, we went from liquid electrolyte to high K dielectric. High K dielectrics are what are used in industry for transistor technology. We could achieve higher mobility. So the higher the mobility is, the better the transistor is. And we could also get very good on-off ratio. So the on current and off current, they're 7 orders of magnitude. That's another metric. So a lot of progress continues on this. Using these transistors now, transistors are using your electronics for making circuits. So we decided to explore circuit applications. One of the most common circuits are amplifiers. So this is a black phosphorus transistor on a flexible substrate. So if you bias it at this start point, you could get an amplifier. So amplifier, the blue is the input, and you can see the red is greater in terms of magnitude compared to the blue. So it provides about 9 times gain. So that's a linear circuit. You can also use this for nonlinear circuits. So nonlinear circuits are often used as frequency doublers or modulators. So if you bias it at the middle point, you could have a frequency doubling operation. So in this case, the blue is the input. So you see the frequency of oscillation, and the red is the output. You see it's oscillating at twice the input frequency. So very versatile transistors. And with this, you can also actually make radio systems. So we demonstrated the first radio. Wayne and Ju, one of my former students, did very good work on this, where she said, okay, to build a basic radio, in this case, a flexible radio, you need a input source. So in this case, we use the iPhone as the music source, and then we broadcast this by AM modulation through a carrier frequency, and then we use the flexible transistor from the studio materials to demodulate. So that means to recover the original sound from the iPhone. And then how do you verify that sound? You send it through a speaker. So here shows the broadcasted music from Beethoven. This is actually you can hear the music coming through this pseudo transistor So we do this quite important. So another application that has been very hot over the last 4 years is for interconnect. So interconnects are how circuits are wired on a microprocessor chip. And so there's a great interest in making this wiring more efficient and smaller. So one of the main criteria for interconnect is how much current can they handle. So we call this current density. So Murali, about 10 years ago, showed that graphene nanoribbons could be very good as interconnects. So it can handle, before it breaks down electrically, it can handle more than 10 to the 8 amps per centimeter squared. So this number is important because it's about 100 times higher current density, breakdown current density, than copper. And copper is, of course, what is used in the current microprocessor technology today. So being able to replace copper with graphene will be very beneficial in terms of reliability and ability to go to superior performance. So we did the first work trying to integrate graphene ribbons on a silicon chip, a microprocessing chip, also about 10 years ago. And so this is actually very complex work, but we managed to do it. And so you can put graphene and get good performance. However, the performance was not as good compared to copper in terms of the resistivity. So we have 2 parameters of interest, current density and resistivity. So while the current density of graphene was higher, the resistivity that we observed compared to copper was not as good. So there's been a lot of research over the last 10 years to improve the resistivity. And so one of those major progress was reported by Costa Banerjee at UC Santa Barbara, where he showed that by doping the graphene nanoribbon with iron chloride that donates charge to the graphene, you can improve the resistivity, and especially for very, very small dimensions, the graphene nanoribbons, which is the blue curve here, has lower resistivity than copper. So lower is better. So this has now catalyzed a lot of industrial effort to try and integrate graphene nanoribbons, especially in small dimensions, to replace copper for better reliability and performance. So the last hot application I want to highlight are sensors. So in fact, we've shown the first sensors several years ago. The publication was a bit delayed, where we use graphene as a gas sensor on top of a silicon chip. So this is the graphene here on a silicon chip that we designed. And so you can send toxic gases. The graphene is sensitive because when these gases interact with the graphene, its resistance changes. So you can measure this change in resistance and correlate the amount of gas you have based on the resistance recording. So this is a chemi-resistive sensor. Our esteemed colleagues, Frank Coppens in Spain, they have shown you could also use graphene as an optical detector, photo detector, and build a camera. So yeah, they use quantum dots to absorb the light. So that converts the light, electricity, and graphene carries this electricity, and then you can construct an image from a two-dimensional matrix. So this is a famous model. They're showing you could even use it not only for normal imaging, but for infrared imaging. And then graphene can also be used as a biosensor. This is actually a product you can buy today from Nanomedical Diagnostics, where you could have an analyte, a biochemical or molecule, and you could sense what is inside. So we've actually now also been working on the biosensors. I won't discuss too much about this, but we're working on a sensor that can detect both the coronavirus and the flu at the same time, because this is the situation that is predicted in the winter when both of these viruses will exist. So using our platform that we developed with collaborators at Covenant University in Nigeria, we published this platform recently. We can use antibodies to functionalize the graphene. So we can use the coronavirus antibodies, and then these coronavirus antibodies, which you can get commercially, will only attach to the coronavirus, and then this is how you detect this virus. You can use the same technique. Instead of the coronavirus antibody, you can use the flu antibody, and then the flu antibody will only attach to the influenza virus, and then you can detect this. So we're building this USB point of care type of device. So now that I gave you a brief history, what about the current and the future? So I'll highlight 4 hot applications. Some of you students in the audience interested in this field, this may be some of the topics that you should consider exploring. So one is negative capacitance transistors. I won't go into the detail, but the main advantage of this negative capacitance is that you can get very, very low energy and high energy efficiency transistors. So the power consumption is low. So that means the battery life for mobile devices, for computing devices, will be lower using this kind of device. So a lot of research in that space. There's also a lot of research for memory. So actually the most important electronic device today is memory devices. So how do we, that's obvious because you need information storage. So how do you use 2D materials for memory is a very important topic. At the same time, memory can now also be used for computing. So most of the computing that is done today is using transistors, but now there's a great interest to use memory for computing because it behaves very similar to how computing is done in the brain. So they call it neuromorphic or brain-inspired computing. And then finally, another hot application, in my opinion, is printed and wearable devices where you can print this on a paper or you can put it on skin for electronic tattoos. So I'll speak now mostly about memory and wearable devices for the rest of this talk. So memory is actually an atomic application of these 2D materials. There are actually many kinds of non-volatile memory, solid-state memory available. The most popular is the flash memory using semiconductors. So that is what is in your solid-state gadgets today, in your mobile phone, in your laptops, and so on and so forth. So I won't speak about this. Now, there's a great effort to replace this flash memory with what are known as emerging memory. So the value of this emerging memory is that perhaps they're going to be much smaller in size than flash memory. So if you can get them much smaller in size, you can get higher memory density, higher memory capacity, which is important for applications. So I'm actually going to focus this section of my talk on this last two memory because this are commonly known as memristors. And so the most popular class of these are based on metal oxides, and sometimes they're called ARAM. So let me use one slide to briefly describe the basic physics of how you get memory effect or resistance switching in memory material. So the actual device is a very simple sandwich. You have a metal at the top, which is also called the top electrode. You have an insulator, a non-conductor in the middle, and then you have a metal at the bottom. So the insulator itself may not be perfect. Indeed, memory is an application of defects. So you may have some limited defects, but the electrical properties of this sandwich as in the initial state is non-conducting. So if you measure the current as a function of voltage, you see that there is no current flowing. So we say that the memory is in the off state. But then what happens is suddenly when you apply a very high electric field, so high electric field between these two electrodes passing through this oxide, then it's a very similar effect actually to lightning, because in lightning you have the same thing. The top electrode in lightning is the sky, and then you have the air, which is the dielectric, it doesn't conduct, and then the bottom electrode is the earth. So when lightning strikes, you get current flowing from the sky through the air to the earth. So the same thing here in a nanoscale object. When you apply the electric field, it's like lightning striking, and these defects align together to form a conductive path between the two electrodes, and then you get current flowing. So we say that this is in the on state. So the remarkable thing about this phenomena is that you can switch between the off and on many, many times. So now you can do it hundreds of millions of times, even billions of times in some materials. So one of the main research areas in memory is how do you make the memory smaller? So you want to go from a big device to a small device, because a smaller device means that you get higher density, so more information storage. It means that it's easier memory to deal with. It's a smarter memory, so it consumes lower energy. So again, that's very important for battery life. And it's also faster because it's a smaller device. So the switching time is shorter. So these are the obvious benefits. But what was discovered is there are a lot of challenges when you go from a big memory to a small memory device. And one of the fundamental challenges is you get very, very high leakage, because these defects now begin to short electrically the top to the bottom electrode as you make it thinner and thinner. So because of this leakage, which is very hard to control, you get lower on-off ratio. So that means the reliability of this phenomena is very poor. And the main reason behind all of these issues is because conventional memory or emerging memory material, metal oxides, are disordered or amorphous materials. So they're not perfect materials. So we said, okay, maybe atomically thin material, these 2D materials can resolve this problem. Instead of using this disordered or amorphous materials, we can go to this crystalline materials that exist as a single atomic layer. They can be as thin as 0.3 nanometers, and you can construct, even in principle, the entire memory from these 2D materials, because you could have a conductor from graphite, graphene, you have insulators from HBN, and you have semiconductors from MOS2. So when we started this research, which was around 2015, nobody had actually ever made this vertical structure, this sandwich, using a monolayer of a 2D material. So I was actually not sure if it was going to work. And in fact, I was quite skeptical because if no one has done it before, maybe there's a reason why. But my student, Wu Jing, who is a graduate of the University of Science and Technology in Hefei, she convinced me that we should at least give it a try. So I'm usually very good at taking the advice of students. So I encouraged her, okay, why don't you try this? This is your first year. And if you're not successful, it's okay. You still have several years of PhD research to graduate. So, so even though no one had done it before, we were actually very, very surprised in a very positive way, where within 6 months, she was able to show actually very good memory. We call this bipolar memory effect in these atomic sandwiches. You have a single layer of MOS2 between two gold electrodes. So we say this is bipolar because originally there is very little current flowing. Then you apply a positive voltage and it switches to very high current. So in the high current, we say that's the low resistance state or on state. And then when you go to a negative voltage, you can reset it to the low current. So it's a bipolar phenomenon. And the retention, that means how long does the memory stay in any state once you take off the power. So when you take off the power, we say it's non-volatile, it remains in the same state. So it can stay there, these are measurements over a week, but now we've measured it for a longer time, so it has very good retention. So we faced a lot of criticism actually initially when we showed this result, because since no one had done it before, there was criticism that maybe our materials were bad quality and this is not an intrinsic property of this 2D material. So we said, okay, that's maybe the case. So let's use other people's materials. So we got this MOS2 from other people, not the one that we make in our lab, from the best suppliers in the world. They're grown in different methods and different thicknesses. And in all of these samples, we could observe this memory phenomena. So now we say this is an intrinsic effect, not an accidental effect. So we call this atomristors because it's a memristor effect at the atomic scale in atomically thin material. So it's just a name to distinguish it as a special type of memristor. And so after showing this in MOS2, we wondered whether we could also see the same phenomena in similar two-dimensional semiconductors. So MOSE2, WSE2, WS2, those are very popular two-dimensional semiconductors, and we see the same effect. In fact, we also did this in HBN, which is the thinnest material, and we see, again, the same effect. So this is the thinnest memristor ever demonstrated. So we've now made an hypothesis that perhaps this memory effect exists in all of these non-conducting two-dimensional materials. So for theorists out there, I encourage you to look into this matter to prove this hypothesis. So one of the areas of criticism and suggestion that we got in the beginning was, what is the mechanism? What is the principle behind the operation of this memory? So we decided to do atomic studies using the scanning tunneling microscope, because with the STM, a special tool, you can do both imaging of the crystal or the device, and you can also do electrical transport measurements. So we took a very clean section of the material that has no defect, and we measure the current versus voltage, and we see that we have what is just a normal diode behavior. There's no evidence of memory effect that should show that kind of butterfly curve. And then we went with a sample that had defects, so the white circular regions here are defect, and then we stationed the STM tip to measure the electrical properties of that defect. And when we do that, we see now the emergence of memory effect. You see there's a window of in the electrical voltage characteristics, which means there's a memory effect. So now we can conclude that defect is responsible for memory effect in these atomically thin materials. But specifically, what role do defects play? So we've now studied this for several, 2 years or so, and now we have a more complete understanding of the phenomena. So when you have a metal and an MOS2, let's say in a sandwich, in the initial phase, it's a high resistance, it's non-conducting. You have a defect, that means you have a missing sulfur vacancy. And then your metal could be gold, for example. So now when you do the current voltage, it's off because there's no current flowing. So when you apply very high voltage through this sandwich, you have some electrochemistry that results in a mobile, let's say, gold ion. So this mobile gold ion has to quickly stabilize itself, and it's going to stabilize itself by absorbing into this vacancy. So when this gold now enters into this vacancy, gold is a very conductive element, so that shorts this material, and then you get very high current. So we say that's the on resistance. So now we have a good understanding of the mechanism. So we're an engineering group. What about applications? So it's not enough for us to do science. Because we're engineers, we also have to try to take this discovery towards applications. So two of the most popular applications for memory is for storage and neuromorphic computing. And so Feng Miao's group in Nanjing has been doing quite some nice work in terms of the endurance. How many times can you cycle this phenomena? So now by partially oxidizing the MOS2, they can get the endurance, the number of cycles, to more than 10 million times. So this is very good, especially for storage applications. Samsung and collaborators have been focusing on using this for computing, neuromorphic computing, very similar to the way the brain does computing. So the measurements here is you want to see, instead of a binary on and off, you want to be able to program the resistance of the memory device by applying voltages. So they showed you could do programmable resistances, which is called potentiation when it rises and depression when it falls. So that's MOS2. There's also been progress with HBN. So, and one group at USC, they are focused on reducing the energy consumption of switching. So by oxidizing the boron nitride just a little bit, they can show that you can reduce the current to the picoamps. So the energy consumption is extremely small, about 100 attojoules per cycle. And then Mario Lanza in Suzhou has done very nice work also with HBN here, sandwiched between graphene layers, and they show you can program how much current or the resistance state of this memory by applying voltage. So a lot of nice results in the last few years. So we have been looking towards new applications. So one of those is for switches. So if you can get these memory devices to switch between on and off and operate up to 100 gigahertz, that means you can cover the 5G spectrum that is of great interest in today's devices. So for the on state, you need the memory resistance to be less than 10 ohms to meet specifications, and the off state, you need it to be greater than a kilo ohm, and the capacitance in the off state has to be relatively low. So when you do this and you combine these two figures, you get a figure of merit that is used to judge how good a switch it is in radio frequency applications. So you want this on and off to give you a frequency that is greater than terahertz or time scale that is less than picoseconds. So we realized our memory devices could achieve this, and in fact, it was also quite simple for us to make this memory device by sandwiching the MOS2 between two gold electrodes. So doing that, the initial measurements were very, very promising. Nice work by my student Myung-Soo Kim. And this radio frequency, so-called S parameter measurement. So this is an on state. You want the data to be close to zero. That means it's lossless. So anything better than negative 0.5 dB is considered very good. And so we get this very nicely up to 70 gigahertz. And in the off state, you want the data, the y-axis, to be as negative as possible. So in fact, anything better than negative 20 or even negative 15 is very good. So we're way below negative 20, even up to 70 gigahertz. So very, very high figure of merit, the record figure of merit in this field. So a lot of interest to now take this basic lab measurements towards applications. So for the sake of time, let me go to my second topic, which is a micro application of these materials. So I'll talk about electronic tattoos. And the main idea is the body is actually an electrical machine. So what does that mean? So if you put electrodes on any part of your body, you can measure voltages and current within the body. So these, you could say, are biopotentials. And so 100 years ago, it was realized that these voltages actually can be correlated with your health. So for example, if you're measuring the voltages from the brain, the EEG, this can be correlated with mental health, with brain health. If you're measuring it from the chest, the ECG, this can be correlated with cardiac health and the heart. So these are using wires. These are definitely uncomfortable. Many of you have already experienced this. It's good for clinical studies, but it's not suitable for portable or mobile health. So about 10 years ago, there was a great discovery by John Rogers, who spoke earlier in this ICANN conference, and Daeyoung Kim and Nancy Liu and others, that discovered that, okay, basically, since all you need is a metal conductor to measure these voltages, you don't really need these big wires. So they invented the field of electronic tattoo, where you put metal thin films on the skin, and with these metal thin films, you can measure the biopotential from any part of the skin and get similar results as you did with wires. So this led to now a field of mobile health or electronic tattoos. So then we wondered and said, well, if all you really need is a conductor, and for mechanical reasons, you want this conductor to be as thin as possible, the thinnest conductor in the world is graphene. So that led us to invent the graphene tattoo with Nancy Liu and Shide Kabiri and our collaborator, Li Tao and others. And this tattoo has the same benefits as the metal tattoo, and additional benefits because it's transparent. You can put it on the skin, anywhere on the skin, and it conforms perfectly to the roughness of the skin, and you can also measure all the biopotentials. We also say it's imperceptible. That means that you don't feel it when it's on the skin because it's extremely light. So with these electronic tattoos, you can now talk about new applications that you couldn't imagine before. So mobile health is one where the data can be connected to a smartphone, human-machine interfaces, athletics, and even fashion. So the way we make these tattoos are actually very simple. We make them on temporary tattoo paper. So this is a tattoo paper. You have the graphene on the tattoo, and using water, you can release the graphene onto the skin. So even high school students can now do this. And then these tattoos are very, very, very flexible. And they don't require any adhesive. Unlike metal tattoos where you need to put a tape to secure this graphene stays well on the skin and can last for about 3 days. So when you're developing a new electrophysiology sensor, you need to benchmark it compared to the commercial standard. So this is just some representative measurements of graphene compared to the commercial. For ECG from the heart, graphene shows similar or better performance. EMG is the biopotential from muscle activity. You can also measure the skin temperature. That's very important for health. And you can measure the skin hydration, very important for skin quality and cosmetics. So in all of this, the graphene shows similar or better performance compared to the conventional standard. You can also do difficult areas of the face, like for example, EOG is the biopotential around the eyelids that measure the retinal or health of the eye. Besides that, you can also measure the movement of the eye. So if the eye is moving up and down, left or right, you can measure this characteristic biopotentials, and you can correlate from the data the motion of the eye. So we decided we can even take this one step forward and use this for control of a drone. So this video shows this subject wearing the graphene tattoo around the eyelids, and based on his eye movement, it can control this drone. There's the signal from the tattoo goes to a transponder at the back of his head that communicates with the drone. So this is an example of a human-machine interface. So this involved undergraduates, and so very wonderful research for students. More recently, we've started focusing on blood pressure. This is collaboration with Roosbeh Jafari at Texas A&M University. And the blood pressure is a very, very important thing for a variety of health reasons. And so basically the blood flows in vessels, And so the blood is a conductor. So if you can measure the electrical signals flowing through these blood vessels with some machine processing and signal processing, you can correlate that to extract the blood pressure. So we've gotten some preliminary results that are already very, very good in terms of the accuracy and in terms of both the systolic and diastolic blood pressure data. And we're doing further trials to improve this with these electronic tattoos. So actually, there's a lot of opportunity for research. So for students out there, if you're interested in this, there's a very nice review paper by Professor Lee Tao Son of Southeast University showing you can use the graphene not just for brain health, you can use it for measurements related to the nervous system, for cardiovascular health, digestive health, chemical measurements or monitoring, physical measurements and monitoring, and electrical measurement and monitoring. A lot of opportunity for innovative research. So I'll now try and summarize in the next few minutes that I have what I have been discussing. So my main focus of this talk is on electronic applications of two-dimensional materials. So the biggest applications by far can be categorized into either heterogeneous integration with silicon technology. So silicon is a dominant semiconductor technology today. So if you can combine 2D materials, let's say graphene and MOS2 and HBN, on top of a silicon chip, then you can realize advanced uses of these materials for electronics, photonics, thermal management, sensors, and mechanical devices. So the industry is very interested in this because this is hundreds of billions of dollars in technology development and business opportunity. So another area which is newer is for flexible technology. We call this revolutionary because this industry is still very young, a lot of room for innovation to make electronic systems on plastics, on paper, on glass. And with this, you can print them like you do paper printing, and you can realize all these new types of electronic devices from tattoos to wearables, smart glasses, and screens. So a lot of opportunity there. Again, for students interested in research and development, this is something you can consider. So I talked a lot about memory. So in fact, there are many kinds of memory. As I mentioned, I only really focused on one kind. This is this sandwich memory, but there are other kinds of memory, phase change memory, three-dimensional memory, and all of these can also use 2D material. So again, for students listening, you find that a lot of opportunity if you're interested in memory research. Memory is the most important electronic device today. So there are also transistors. I mentioned briefly many types of transistor structures, and there's a great interest to integrate these transistors onto silicon chips so you could have graphene and two-dimensional materials combined with silicon to form advanced microprocessors. And these different transistors can have different electrical properties, and some of them can even be useful for quantum computing. So with that, I'd like to acknowledge my team, students and postdocs. This is a bit older picture, but as a university professor in America, my job is really, I can say I am a PowerPoint engineer. Actually, the students do all of the work, so I thank them very much for their hard work. And then our collaborators from across the world at UT Austin, in Europe, in China, and in Asia, we're very grateful for their contribution in our collaborative projects, and also our various sponsors, from industry sponsors to private foundations and to government sponsors. These are very important for doing research. And then I would just like to conclude by just highlighting the importance of education for individual development and for the development of society. In engineering especially, it is valuable to not just have technical courses in materials and science, but also now to have entrepreneurial courses which can enable individuals to take innovative technical ideas towards business opportunities to benefit society. In this regard, I want to emphasize, as I wrote in this article, which you can find online, that to be successful in research and development, one also has to embrace failure. So to the student audience, I want to encourage you, don't be afraid to fail, because this is really the path to discovery. So with that, I thank you all for your time, and I'll be very happy to take questions at the moment. Thank you.
All right. Okay, now let's take questions, and then we'll have that. So first, Professor Deji Akinwand, so it's very nice talk. Graphene is very hot topic in the last 15 years, like you said, about 60 paper publications per day. So how about the commercialization, and which will be its killer application? And then the second question, in China, many groups are working on this too. So do you have any collaboration or projection on this?
Yes, so for the first question, indeed, this is a question that we have been asking, and everybody has been asking for the last 10 years. What are the major applications of graphene and 2D material? So there are already some applications of this materials already being used today. So some of these applications are in composites, where you mix graphene with other materials to get stronger or better materials. So those are used increasingly now in many cell phones use the graphene for spreading the heat in the packaging of the cell phone. So that's an important application. So some other applications like bicycles and cars are using graphene to improve the strength while reducing the weight of these bicycles or cars. So those applications also exist. Then some applications, there are companies doing the graphene for sensors. You can buy these products today for biochemical sensors. So there are those applications already. And then there's some new applications that still is under development, and that is to combine graphene with silicon technology for microprocessor and semiconductor technology. That's a bigger market and requires much more development. I would say across the world, there's a lot of this development is being done in Europe and even in China. China invests probably the largest amount of investment for development of graphene-based technologies. So I think there are many experts in China that can speak about this.
Great, thanks. All right, so let's see what's the second question. So it's wonderful talk. This is Liu Han Li from Beijing University. I'm saying which university. So now you mentioned the use of flexible devices in the radio frequency circuit. So would you please explain the circuit structure or the configuration? So is that the flexible device can act as a microphone? So is that clear?
Yes. So with this two-dimensional materials, you can create flexible devices. And so in fact, you can make many, many flexible components, so you can make flexible system. So the two-dimensional materials like graphene and MOS2 can give you very high speed, high current to flow in the flexible material. So you can make a transistor. The HBN can be used as a gate dielectric and also to manage the heat so that it doesn't damage the flexible substrate like plastic. And so you can make the transistor. As I showed, you can also make the memory device, because for a flexible system, you not only need to make transistors for microprocessors, but you also need to make memory for storage and computing. So you can make the transistor, you can make the memory, you can make sensors, you can make touch displays on the flexible device with these two-dimensional materials. And you can also make a microphone and a speaker from graphene. And in fact, very nice work has been shown by researchers from Tsinghua University, Professor Tianling Ren, showing that you could make a speaker from graphene on a flexible substrate. So basically, your imagination is the limit. Anything you want to make on a flexible substrate, mechanical devices, you can actually realize them with these two-dimensional materials.
Okay, great. Yeah. All right. So let's take the third question. So as a channel material, as a sensor, so what kind of advantage does graphene have over the other two-dimensional materials?
Okay. So yes, this is a very good question because there are a lot of two-dimensional materials. So we need to understand which one of them is best for a given purpose on a flexible substrate. So for example, if you want to achieve terahertz operation, so very, very, very high frequency applications in the terahertz. So terahertz is useful for security and for imaging applications, let's say at the airport or for food monitoring. These are using terahertz to frequencies for these operations. So you need a material that can go to this very high frequency. So graphene has the highest mobility. That means the electrons are the fastest in graphene. So for terahertz applications, graphene is the best material. Now, if you're looking for gigahertz, so lower frequency, let's say 1 to 10 gigahertz, and you also want lower power operation. So MOS2 is a very good material for that because it's not as fast as graphene, but it's fast enough to give you gigahertz and also give you low power. Now, if you're interested in 5G, for example, millimeter wave, so somewhere between 10 gigahertz and 100 gigahertz, other two-dimensional materials are useful there, like black phosphorus can be used because their speed is between MOS2 and graphene. So based on the speed of the material, electrons, you can decide which one of them is best for a given frequency of application.
All right, great. Yeah, I guess so it really depends on the application to choose the best material. Okay, so the fourth questions. So are there any oxidation or degradation during the use of 2D materials, and how do you comment on their lifetime?
Yes, so this is a question that is basically related to the reliability of these materials. So different 2D materials have different, I'll say, air stability or chemical reliability. So graphene is very, very stable, probably the most stable of the materials, graphene and HBN. They can resist oxidation in air, and they can resist it even to high temperatures. Some other materials are much more reactive to oxidation. So MOS2 is a little bit reactive to oxidation. So if you want to use it in an application, you probably cover the MOS2 with a protective layer, a thin film that will protect it from the environment. And then in this way, to be very stable over a very long time. Some other 2D materials are much more sensitive, like silicene, made from silicon atoms, or phosphorine, made from phosphorus atoms that I mentioned in the beginning. And these materials are extremely reactive, even at room temperature. They can oxidize, and then you lose the 2D material. So in those cases, you need to spend more energy to come up with very, very effective protective thin films that can protect them from the environment. So when you do this, then these materials become stable. So there's a lot of opportunity for chemical engineers, material science, to work on this kind of protective layers to allow the material to survive over a long time for the duration of the application.
All right, great. I guess that will be the last question. So is it possible to integrate graphene into conventional IC circuits as a mass production level?
Yes, well, you know, we're optimistic this is possible. So you, first of all, the commercial IC is a very big business. We're talking about hundreds of billions of dollars. And so it's not easy to bring in a new material into such a sophisticated facility. Nonetheless, the major companies, all of them have invested significant effort to bring graphene and integrate it in a commercial IC. But it has to go through many, many levels of requirement and development. And so this is an ongoing research and development in these commercial companies. And this is going to take some time because they need to make sure that it doesn't compromise their business, which is hundreds of billions of dollars as they try to introduce this new material. But I believe that it's going to be realized. European researchers and companies have invested a lot. There's a lot of activity in Europe and also in China, in Japan, and in Korea. And even in the US, we're doing significant work trying to integrate this material. So this is very multidisciplinary work. And indeed, many students that are graduating working on 2D materials, going into industry, they're going to work in those areas of development to bring 2D materials on an IC chip.
All right, great. Thanks, Deji, for the talk and some answers to the questions. And for the time's sake, we will only have this time. And now I think Alice wants to deliver the certificate to you. So Alice, please.
Okay, thank you, Lee. Tao Lee is a very wonderful, hoster. Yeah, you really did a good job. So, Deji, that's for you. Certification in IKX tasks. So, using a technology to connect the world and universe. Yeah, it's a wonderful job. Actually, I still have a question here for you. Yeah, in your slides, you mentioned that you use graphene to make 100G, the device. That's amazing. I think a speed is so high. I wondering how about the heat transportation, in the device, and how about the power consumption of this such kind of device. Can you, give some comments on this?
Yes. So the power consumption is also high, especially when you go to high frequencies. You consume more power. So that is something that one has to deal with. And then the heat dissipation is also quite high as well. But the good thing about graphene compared to other materials is it's a very, very thermally conductive material. So as it begins to consume more power, it can dissipate the heat, maybe to the contact or the heat reservoir, and then that can allow it to operate over a high temperature. So even when it's very hot, as it's operating, it can rise to 300 degrees C. It has very high thermal stability in air. So it resists oxidation, so it can operate. Some other 2D materials, when they get hot at this kind of, let's say, temperatures, then they become more reactive and then they begin to oxidize and then you lose the function. But graphene is much more stable, so it can operate while consuming a lot of power under a bit of a high temperature and still resist oxidation, so you can get the function in these conditions.
Okay, great. So, that's very important. I think in the future, as in the last question, I may, have some kind of my ideas here is for if not merge this, kind of 2D material fabrication into commercialized IC. But maybe this can open another window, like more than more, right? Yeah. So you have more function and some new approach to solve the problem now IC was facing. Everyone knows that Moore's law is, getting a big challenge here. You go down 1 or 2 nanometers, for the this kind of fabrication. Maybe it's not necessary. You use graphene or other 2D materials, you get more functions, right? You change the play, the gameplay, kind of the gaming. Yeah.
Yes. This is one of the areas that, in fact, they want to integrate for 3D integration, and then you can get more function per unit area compared to what they're doing right now. So yeah, this is very important.
Okay, great. So now we need to move to next, kind of, we have the dialogue. Actually, I already asked a few questions before this. Well, on this dialogue, we will talk about the adventure from micro nano to atom. We invited our next speaker, Kaheka here. We invited Paul Lee to join this, dialogue. We will talk more about this. Okay, welcome everyone. Yeah, I'm so glad to see all of you here. Looks like, I'm okay. I'm come back. Okay, yeah. So it is very great, Tahek. Yeah. So welcome Tahek. Professor Tahek. Yeah. So just now we talk about the 2D material, graphenes, to try to, move forward to solve the problem for the Morse law. You did a lot of work in MEMS, right? In micro and nano field, and you do a lot of things for commercialization. I think I want to first to hear, we continue that discussions is what's your opinion to, to solve the problem or challenging the Morse law? Yeah, to using maps or others to get more functions. Is that possible, to enlarge the area and enlarge the field? Yeah, based on your experience. Yeah.
Yes, thank you, Alice. I think in my case, I'm starting from the micro scale and going up to other scales, city scale and even global scale. So, of course, what I try to contribute is to bring this MEMS technology address novel applications, which I will have the privilege to introduce in my talk today. Yes, so that's.
Okay, really, yeah, I realized that you did a lot of work to merge, the maps technology with the existing, the technologies. Like you make something as a product with my cell phone, right? Yeah, to detect the food quality, all this kind of thing. I think this give us a lot of thinking, so we can use this new technology like get new functions to reach all these kind of IC devices, right? Yeah, not only just based on IC devices, they can, do some processing, do all this kind of data calculation or something. Also can add in more things like maps sensors, right? Even gas sensors and all these kind of different sensors to get the pictures more larger.
Yes, absolutely. Absolutely. As you know, MEMS started already more than 30 years ago, and it took some time to get mature technology. So I believe those fascinating technologies that were described by Deji will find a fantastic application within the next few years.
Yes, yes. Based on this, sounds Deji, your graphene was popular for 50 years. Now maps was popular for 30 years, right? Yeah, we're all on the way. Yeah. So good. Okay, back to the dialogue about tonight. I think first, maybe I have some kind of comments for Deji because in last 1 or 40 days. In the whole world, everyone was talking about one name was Floyd. And I saw he was from not Austin, he's from Texas, right? The same state where you're from. So it's a really sad story for I couldn't breathe. I think the whole world is, say something for him. And so you're from the same state. So did you have any comments for this?
Yeah, Alice, thank you for bringing this up. You're talking about George Floyd, who suffered police brutality, and this is a situation in which many Black people have suffered and increasingly suffered for a long time in the U.S. So it's really a very unfortunate situation, a very special social issue. So I thank you, Alice, for bringing it in this international forum. I guess I'll make maybe 3 comments regarding this important social issue. It is very important, I think, for everyone to realize that Black people matter. The future of the world, according to population statistics, will consist of a large population of young Black people. The kindness and talent of Black people will be necessary to make our connected world a happier and better place for everyone. The second comment I'd like to make is for education. When people say Black lives matter, it doesn't mean that other lives don't matter. In fact, all lives matter. What is meant is that Black people especially suffer a high level of persistent discrimination and injustice in the United States and other countries, because of the color of their skin. It is time to come together to overcome this racial injustice, and people all ultimately should be judged by their character and their talent. And finally, as an American, an African, Nigerian, and a Black person, I want to say thank you to all those supporting Black lives, minority people, women rights, people with disabilities, supporting them all over the world. Thank you very much for your support, because it's important that we all come together to overcome injustice. Thank you.
Okay, Deji, don't worry about that. You get the whole world support. Yeah, I think you are the big examples. Several years ago, you remember I met you in the IEEE conference. The first minute, the first shot I saw you, I love you because I love your energy, talent. I love all the things you bring to us. This kind of happiness. That exactly that's my first feelings. I think in this kind of international level, the whole world, everyone agrees that the peoples go together. It's based on their character. On this going to share, they're going to help each other to get better life, right? Yeah, we can contribute in academics and technology part. Other people's, they have talent, they music, they have talent, they different areas. They all contribute. Yeah, that means which one is better, which one is not, very good, because everyone contribute their own talent, do their own, best to, make efforts to do that. I really, really think, we support this fighting. Yeah, we want to, give everyone the same chance in the same world. And this year, ICANX is such a platform. We based on the peoples. You did good job, no matter where you're from and who you are. If you did good job, you are going to share. You're welcome. So yeah, Deji, you're welcome. So Professor Tahik, so you're from Europe. I saw you have many students from Africa, right? From a different place, and you also nursing them to become superstars. Yeah. So you did a wonderful job. Can you have some thing to share with us based on this?
Yeah. Actually, I took students from whatever from where they come from, maybe 15 countries. I had students in my lab, but these are facts that I have a kind of privileged relationship with a university in Egypt. It's Ain Shams University. I'm working closely with colleagues since almost 20 years. And I took a significant number of students in my group. Some of them had very successful paths, either in academia or in companies, establishing companies. And other students also came from other parts of the world. One of them came from Lebanon, and he established one of the first MEMS company. His name MEMSCAP.
Everyone use that.
Yeah, he used to be a student in my university, and he was very lucky in his path, trying to do optical MEMS just before the telecom crash, the first telecom crash, the dot-com crash. He entered the stock market, and then after that he gained a lot of cash. Just before the crash. It was lucky for him. Yeah. But unfortunately, he was not able to continue what he was intending to do in optical MEMS for telecom. Then he moved to other directions, and his company is still sustainable with more than 100 employees. So I will tell about other successful stories of students doing MEMS in my presentation.
Okay, great. Thank you. I know you have a lot of Chinese students too. You nursing them very well. Yeah, many of them moved back to China, and even they work in France or in other, countries. That's really
that's
good
true.
for the education. Like Deji say that education is to nursing the people, no matter where they're from, but they, build up their career, build up their future. Tao Li was one good examples, right? Tao Li was Chinese talent and then go to US. You are, have some time with Deji, and now you also have good collaboration. I saw you have a very close relationship with different, peoples, right, from different nationalities. So, yeah, could you please share your stories with this as you are, in the overseas, deal with different peoples? So, Lee, did you tell?
Yes, yes, it's on. Okay. Yeah, thanks, Alice, and thanks, Deji and Tariq. I want to thank that I do have this opportunity, as Alice mentioned, to go abroad to work with these, people from different culture, different nations, different backgrounds. I think this really made me learn a lot and do what I can do today. And I just want to make one comment that we should give all the bias to the devices, which we need the bias to work, but to get rid of the biases in our brain. So we should get rid of the bias, then we can open our mind so that we can work with other people and leave all the bias to the device where it needs, right? So, and that's just like one comment I would like to share with the audience. And also, I think I really like the last slide that you mentioned about the education, how to deal with frustration and failure during the PhD research. I think that probably something useful for the audience. I'm sure there's a lot of students here, and I'm sure at certain stage of their research, they always get, frustrated and even want to quit their, PhD journal or turn. So I think that we really need to, stick on it and get bottom of the sign and get bottom of this technology and try to move on with, persistence. So I think that's all I want to share. Thank you.
Okay, great. Tao Li got the right mention. I want to, go further in this dialogue and this part, because Deji's last slides, especially his words, you must, accept the failure. Right? You must deal with the failures. Actually, in one article, I forgot which one said that, how many percentage for the, PhD students, they had some trouble here in depression or something, because that time is really hard. So I think, Deji, you write that very good articles, on time. So, could you please give us more stories how to deal with, the big challenge, the frustration, the failures, in your life? Did you have such kind of story to share? How you overcome? How you, save yourself?
Yes, I mean, in our research, most of the results are always failures. And so eventually we learn from these failures and we become successful. So I think this is very important, not to see failure as a failure, but to see failure as a teacher, teaching us how to do things in a more correct way, or teaching us the ways that don't work. So, of course, one of the most famous example is the invention of the light bulb by Thomas Edison, who tried, hundreds of experiments that didn't work, but eventually he figured out a way to make the light bulb that worked. So each experiment was a teacher telling him how to make something better. Even in my lab, our first flexible device, which Li Tao is very familiar with, my student, Jong Ho Lee, it took him 15 experiments to make the first flexible device. Each experiment takes 1 month. So it took him almost 1.5 years. And every month for 1.5 years, he failed to make the device to work.
Wow.
But every time he learned and he was persistent. So of course, with failure, if you want to learn from failure, you have to be very persistent and not give up. So eventually, after 15 experiments over 1.5 years, he could learn how to make it successfully. So then the next time to make the device only took him 2 weeks, and then it took him only 1 week. He became very good. He could make the device in just 1 week. And so I'm also reminded of my son. My son, when he was a child, to play with the smartphone, you don't teach a child how to play with the smartphone. They figure out how to play with the smartphone. So they can figure out how to unlock the smartphone, how to press the right button to get games. And so they play and fail until they say, okay, if I press this button, then I get to the games I like. If I press these buttons, then I unlock the phone. So we have to look at failure as a teacher, not as a bad experience. And when we do this, we can learn from failure and we can find maybe the right way to discovery.
Okay, great. Yeah, everyone think, if you think this way, you gain more from your failures, right? You not got more frustrating, from your failures. You got, more kind of information from that. So, Tahik, since you from travel from at several countries, I think many things you have met. Yeah, in your life, go Paris and you Japan somewhere, so you should met many things, even some really challenges. How you deal with that?
Yes, absolutely. Yes, of course, I had multiple experiences overseas, and also I hosted the students coming from different parts of the world. And it was always a very enriching experience, human experiences with mutual benefit. Most of the time I learn from my own students or my own collaborators. And also it was an opportunity for cross-fertilization, and having experience overseas is always very enriching. So I loved all those experiences, either in Japan. Also, I spent some time in Singapore, and more recently launching new collaboration in China, and of course sustaining this long-term collaboration with Egypt. So this is a lot of different cultures, and this is very enriching indeed.
Oh yes, so you are really good at that and handle all these challenges, right? Yeah,
yes.
That's
Also,
once you
Yeah. Also, what I would like to highlight in my my own environment here is that the School of Engineering, where I used to prepare my PhD, and now working after more than 30 years, is a very special ecosystem, because instead of being under the Ministry of Research of Education, it is under the Ministry of Industry. Somehow is called the Chamber of Commerce and Industry, and it is in our mission to be very close to companies and to support the development of companies. And when students are this kind of environment, they are aware about the needs of the companies, and this can speed up the time to market of their innovation. So and in the same time, being in a university environment give us a kind of seed for knowledge and technologies that could be brought into applications.
Yeah, this also can solve some problems, because many students they are really struggled, because after graduation it's hard to find a job. But if they are in this ecosystem, they already did something, connect with the industry, or even, put some kind of results, go to the market. That's really, no problem for the job hunting, right? Yeah, because everything
Yes.
was there. And even they got the job, in their own company. Yeah, so many of your very good stories for students to set up your own startups. That's very good. Yeah, we're going to have your stories. Yeah, in your story, in your presentation. Here I have a comments for this is based on my experience in ICANN. ICANN was a contest for the innovation to promote students and to push the students to do something. Yeah, in ICANN for last since 2007. Now it's 14 years. Yeah, it's pretty long time. So I deal with many, almost millions of the students. I saw all these, growing paths. I choose 3 keywords: how to deal with your, growing, and how to deal with failures, how to deal with all these kind of challenges. 3 keywords. One is confidence. You have to be more confident. You should, trust yourself. You can do something, and you can get something done. That's the first keyword. Is you must be very good, self-confidence. That's one important word in your mind. The second word is persistence. No matter what kind of challenge you failure or you met, you think you are maybe the most kind of black days you gone through, but you must, like Deji said, his students never give up. Yeah, I just, go ahead on this direction, never give up. So that's the second word is persistence. You have to, keep on going. Then, eventually you'll get something. The last word is dream. You must have a dream inside, which the power source for you is your dream. Because you have a dream to achieve something. You have a dream to solve some problem, to make the world different. If you have this, kind of dream inside, your power will never be, failing. So if you don't have such kind of power, you're driven by money or you're driven by other kind of fame or something, it will certainly, be, gone away very soon. But you have some dream, you try to, build a different world. You try to, get some different things. If such a dream inside, I think that's really the power source, the nuclear place, right? Yeah. So that's my experience in the last 14 years. So I can tell the students, okay, if you want to go further, to get a better life, to feel good, okay, keep these 3 words. First is self-confidence. Second, persistence. The third one is keep your dream. Have your dream. Never, be faded by others, My dream is my dream. I will continue with this. So these 3 words, I try to, every day, I repeat. So this morning, I also give a talk to, another kind of university level, the students. I say that every day, repeat these 3 keywords. So you will never be failed because yes, I can, right? Yeah, that's you get the keywords. So I think for most of the students or the young, faculties or even the scientists or researchers or even young people, listen to this talk, be sure to, learn that. As Tao Li was one very good word is, bias. It's just keep it on the wafer, right? On the devices that use it as a connection. Never use bias in your life because that's not very good. Yeah. As Professor Tehig said, no matter he go anywhere, in the whole world, that's a universe, to accept, to deal with this and to get good friends, to figure out with you. Deji is, already write the articles for you. So be sure, go back to read all these articles, right? Yeah, keep the keywords. That's very, very good. Okay, I think we need, go further to, this adventure. Yeah, so we will, continue this kind of dialogue in the ICANX talks. I think every week we try to give something or deliver some message from different speakers from a different, place. So thank you, Deji. Thank you, Tao Li, and thank you, Tahik. It's very good to meet you, on this ICANX. Yeah, live talk. So we will continue for Tahik. Yeah, Tahik's talk is going to, be micro and nano. Yeah.